Hi, my name is Mitchell Clark, and I'm one of the ECEN 325 TAs for the fall 2024 semester. This is going to be the Lab 10 Hints video. So the primary goal for this lab is that we are going to be trying to introduce the MOSFET transistor, also known as the metal oxide field effect transistor. And we're going to try to characterize the device and kind of see what the differences are between it and the BJTs that y'all have been used to in this class so far. Alright, so what exactly is a MOSFET transistor? Well, it works more like a voltage-controlled current source, where we modulate the voltage that's going to between the gate to the source so that we can alter the current that flows from the drain to the source, right? And physically, this looks like the depiction here on the right? So we have a sort of a p-doped silicon region, and then we have two much larger n-doped silicon regions, where the drain and the source connect to there. And lastly, we have a metal plate up here, usually like aluminum or some other material that the gate attaches to, with a dielectric here in the middle. So you can kind of think of it as a gate capacitor between here to the gate and to the rest of the MOSFET device, right? And the idea is that when we apply that voltage from the gate to source, we apply that voltage to the gate here, right? And then this is a p-doped region, right? So it's full of holes, right? And by applying that positive voltage, we push all the holes away down further into the rest of the device, leaving just a bunch of electrons up here, closer to the gate capacitor, right? And what this does is that sort of bridges the gap between the source to the drain terminals, creating what we call a channel right here, okay? And then by applying a drain to source voltage as well, right, then the electrons that exist in this channel are forced to move, which creates the current that we're talking about, right? So the gate to source voltage is what sets like the size of the channel basically. So that's going to be the more dominating factor as to what determines the current, right? But then the drain to source voltage is what sets sort of like the speed limit, right? So it can also affect the current as well, but the primary indicator is the gate to source voltage. And as we'll see later is that there are operating regions similar to BJTs, where if the gate to source voltage is a certain range or the drain to source voltage is a certain range, then the device is going to act differently depending on the sort of current that it outputs. So we mentioned before how MOSFETs and BJTs are similar, right? But how are they different? Like, why are we trying to learn about them separately from BJTs, right? So as I said before, MOSFETs are more like voltage-controlled current sources, right? So by modulating the voltage from the gate to the source here, we can determine what the current going through the drain to the source is, right? Meanwhile, for a BJT, right, we set that 0.7 voltage drop, or we keep the voltage drop about the same, and then by applying a certain current here into the base, then we can control the current flowing from the collector to the emitter, right? Now, another important detail as well about MOSFETs is that there is not going to be a gate current, right? Because there's this gate capacitor here, so it blocks the DC currents, right? And this will also be later reflected when we get to the small signal model for MOSFET, because what you'll find is that there's not going to be any gate to source resistor. So arguably the small signal model for MOSFETs is actually much easier to use. Now, if you're in a situation where you're trying to choose between one or the other technologies, it's kind of hard to say which would be better. And this is something that's been debated for as long as since these different technologies have been a thing, right? In the context of IC design, right? Whenever we talk about CMOS, right, or metal oxide, sort of MOSFETs, right, and then we talk about bipolar, referring to BJTs, right? These technologies, they've been evolving for so long, meaning that their various weaknesses have been improved upon and their various strengths have been shot up as well, right? So overall, whenever you're trying to decide what situation, which technology you're going to use in a certain situation, is basically depends on what the specific parameters are of your technology, right? So this is why we characterize the MOSFET in the BJT devices, right? Because we're going to get an idea of, how does it act in certain situations, so we know how to make a decision, right? But then, even then, if you're working for a company or on some sort of research, usually you don't really get much of a choice about which technology you're going to use, so that's just kind of what you got, right? Now, talking about the differences, right? This has been debated, right? So for example, pulling from some textbooks, right? So this is from Kamenzind, right? He's the inventor of the 555 timer, which you might have heard, and is in this 2005 textbook. He generally talks about how BJTs are superior devices, right? They've got much lower noise, right? CMOS devices are less, like smaller themselves, right? But in order for them to work properly in analog, they have to be scaled up, and they're going to be about the same size anyways, right? And then BJTs are also a little bit generally better at like low voltage designs, right? But in another example, we've got Razavi. Razavi is arguably, one of the greatest analog designers of all time, right? In his 2015 textbook, talks about CMOS, right? That CMOS is pretty much strictly better for like digital devices, right? And we try to design analog devices in the CMOS technology as well, so that we can put them all on one chip. Though nowadays we have something called bi-CMOS processes, so we can put MOSFETs and BJTs all in one design if we want to. But also another thing is that like CMOS is, much cheaper as well, right? And can be scaled to be much smaller as well, so the individual devices don't have to be as big, right? And they can also operate at lower supply voltages, which you can see 1 volt versus like 2 volts for BJT, right? Because we can just make the device larger if we need to, right? Which you'll see later in the IV curves, right? So if I had to try to summarize sort of what the difference is between these two devices, right, is that I think BJTs have generally better analog performance, right? They're more desirable for power circuits, and they're generally faster than MOSFETs because they don't have a gate capacitor, right? But MOSFETs can be scaled to much, much, much smaller individual devices. They work at much smaller voltages and are also much cheaper to fabricate, right? And these qualities combined with the fact that they're great at switching makes MOSFETs strictly better than BJT for digital designs, right? But for analog, though, I don't think MOSFETs perform as well as BJT devices, but because they can be made so cheap, because they can be scaled so small, right? These are also pretty desirable qualities for, analog design as well. So that's just kind of the trade-off that we'll take. So now let's kind of get back to how MOSFETs are similar to BJTs, right? So one of the main comparisons is that MOSFETs also have operating regions, just like how BJTs work. And a lot of the quantities that are in these operating regions have similar analogs to what we see in BJTs, right? So for example, MOSFETs also have a cutoff region, right? So instead of MOSFETs having like a 0.7 voltage drop from the base to the emitter, there is a sort of a threshold voltage from the gate to source, right? So for small technology processes like 40 to like 180 nanometer or like 40 nanometer, right? In general, this value is going to be about 0.5 volts, right? So if the gate to source voltage does not exceed the threshold, then no current is going to be allowed to flow, right? Then we get into the triode region, which is similar to the sort of like the linear region that you see at the beginning of the BJT curve, where, okay, now our gate to source voltage exceeds the threshold, but now our drain to source voltage is not high enough, right? So if you remember how for the BJT, right, we could meet the 0.7 voltage drop from here to here, but then that saturation voltage, that 0.2 voltage, if the collector to emitter voltage, right, was less than that saturation voltage, then we were in the saturation region, right, that linear region, right? This is the exact same thing that's going on. So now what we're concerned about is that does the drain to source voltage exceed the overdrive voltage, where the overdrive voltage is just, okay, how much does the gate to source exceed the threshold voltage, okay? And if it exceeds by a certain amount, then the drain to source voltage, in order for it to go into active region, has to exceed this overdrive voltage. So when it does not exceed the overdrive voltage, is described by this equation right here, okay? And reading this equation, the k prime of n, these are just like constants, basically. So this is a value that you would have to find when doing your characterization, right? This just comes from the device science, right? And then we also have this w over L right here. And this refers to the size of the gate, right? So for example, we have our depiction up here. This is like a side cross section, right? But looking at it above for a MOSFET, right? we have our drain here, and we have our source here, right? So we have the length of the gate here, which means like how long does the channel have to be to span the two sides, right? And then you have the width over here, right? So how long is the channel going to be in the width dimension, right? So having a longer width means that more electrons are allowed to flow through. So larger width means that the allowable current goes up, right? But having a longer length means that the channel has to be longer. So it's going to overall reduce the current, which is why it's at the bottom here. Okay. So then, as we were talking about before, okay, if our gate to source voltage exceeds the threshold and our drain to source voltage exceeds the overdrive, then now we're in the active region, right? Which is also called saturation region. So don't get that confused with the BJT, where saturation region refers to the linear region at the beginning, but for MOSFETs it's called saturation region, which is the ending part, the active region that we were desiring to use whenever we were designing our amplifiers, right? So this is going to be the amplifier region that we want to put things in whenever we want to build, our common gate, or like in this case is going to be our common gate and our common source and our common drain amplifiers, right? So it uses the exact same kind of constants as before, right? And then the equations are right here. So when gate to source is greater than threshold and drain to source is greater than the overdrive, then now we are in the saturation region, right? And then looking at these depictions down here as well, these are common symbols for how we describe the MOSFET, right? So you're probably going to see this one a little bit more often in this class, right? But there is actually a fourth terminal to MOSFETs called the body, right? Which is actually, if you look at our picture right here, is going to be referring to this area down here. But for our purposes, usually the source and the body are shorted together on the like the discrete devices that we have. So we're not going to talk about the body too much, but just it's something to be aware of, right? Whenever you see these depictions, right? And then once again, just like BJTs, right? MOSFETs do have an NMOS and a PMOS version, right? So where the doping regions, like in our depiction, would be flipped, right? And then we have all those relative equations here for us, okay? One quick thing of note as well about the PMOS devices is that the threshold is going to be negative instead. Okay, so just be sure to watch out for that whenever we model the devices later in Multisim. Okay, but the absolute value is going to be about the same between the NMOS to the PMOS devices. Let's bring the comparison a little bit further as well. So for example, on screen right now, I have the BJT collector current curve, right? Talking about, as how the collector to emitter voltage varies, what do the operating regions look like? And this assumes that the base to emitter voltage is already 0.7, right? So we have the saturation region, which is that linear region that we're talking about. And then we have the active region over here, right? And then later we also have the breakdown region as well, which does exist for MOSFETs because you can apply too much voltage such that it just breaks the device, right? And then comparing it to how the MOSFET collector current curve looks like. So remember, now we're not on an exponential curve anymore, right? You might have noticed about how MOSFETs are on a quadratic curve, right, instead of an exponential curve. So the plots are going to look a little bit different, right? So now we still have our linear region, right, which is when the gate to source exceeds the threshold, but the drain to source does not exceed the overdrive, right? So you have the sort of linear region right here, and then eventually flattens out, and the saturation region over here, which is when the gate to source does exceed the threshold, and the drain to source voltage does exceed the overdrive, right? So you can see how we get that flat curve at the end there, which is going to be great for the amplifiers that we want to design later. So now let's talk about characterization, which was the goal for this lab, right? So remember, if you remember our conversation talking about BJTs, right? The reason why we do MOSFET characterization is because depending on the devices, right? Whether it's a technology or a discrete device that you get, you need to test it to see how it acts, right? Because different MOSFETs are going to have different operating conditions and different, transconductance levels, right? So we need to try to do these measurements to characterize and understand the device that we're going to be using, right? So in the lab manual here, they give us what the setup looks like for the NMOS and the PMOS respectively about, how we're going to set up the proper voltages to then sweep that gate to source voltage and then see, okay, what do our drain current curves end up looking like, right? And remember that we do this is that because we can try to obtain what the threshold voltage is and what the transconductance is, right? This parameter right here, we're talking about how was constants that we don't really have control over, right? We can obtain what those are in this curve, right? Which you can see sort of the depiction below, right? So in Multisim, you'll set up this circuit and then perform the sweep of the gate to source voltage, right? So just sweep this DC source right here, right? And then once you plot the drain current versus the gate to source in Excel, then you'll get this curve right here. And then what we like to do is that if you take the derivative of that in Excel, right? So if you just take the point-wise derivative, right? So do rise over run between each point in Excel, right? Then you can get this sort of derivative curve, right? Where you'll find where the derivative begins to rise is the threshold voltage, right? And then the slope of this curve is what gives you the transconductance parameter right here, right? Now, unfortunately, whenever you start plotting things in Multisim, you might not get as nice as a curve like this, right? And especially if you're using a much more advanced simulator, then you know, things might not look as nice, right? Because they're going to be modeling much more like second order effects, right? So if you want to really get specific, right? For example, if eventually you take ECEN 704/474, there's a little bit more of a complicated process that we actually go through, right? So this is talking about the exact same thing. So just look at these two plots up here. Don't worry about this one down here. So you have the same drain current versus the gate to source voltage, right? And then you'll see, right, that when you take the derivative of it, then you end up getting this sort of curve right here, where the tangent line right here, right, where this tangent line occurs is at the max of the second derivative, right? So d squared over d. So it's at the max of the second derivative, right? So your second derivative curve is going to look like this, right? So you find the x value where the max occurs at, and that's going to be where the tangent line of the slope that we're talking about is, right? So then you can go ahead and backwards calculate this little mu cox right here. That's k, right? You can find what the specific point is on your curve in Excel, right? And this way you can get a much more precise definition for VT and the slope right here. But that's a little bit extra, right? That's looking a little bit ahead, right? But if you're able to produce this curve right here, right? And then just sort of guess, find what like the maximum slope is along this line, then you can use that to approximate what your transconductance parameter is, and then you can calculate what the VT as well, right? So this is a little bit extra if you want to get really precise, right? But this is all that's expected for this lab. So now let's talk about the simulations that you need to do for your pre-lab. So many of y'all will be happy to see that we're not doing any calculations, right? But the first thing that we need to do is that there's not actually specific components in Multisim for the devices that we have access to in lab, right? So we have a custom MOS transistor library that we're going to upload into Multisim to use, right? So if you end up going onto Canvas, right, at the very bottom with the modules, right, you should be able to find the user comp underscore s underscore ecen.usr, right? So you're going to want to download this file, right? And then you're also going to want to pull up the custom model instructions PDF, right? So when you pull up this PDF, it goes through exactly the step-by-step process of how to install this file, right? So keep in mind this little warning right here for people that use Multisim Online, right? Make sure you use the virtual open access labs, or make sure you have the software downloaded on your computer, right? So then what you're going to do is that once you've downloaded the file, right, you're going to go into Multisim, you're going to go to options and then global options, right? And then you're going to add your file, right, here under the user database right here. So you can click this button to go to your file explorer, and then you're going to add it there, right? Now, I've had multiple people, including myself, having some trouble getting this file to actually show up in Multisim once you've uploaded it, right? So my recommendation would be is to probably change the ECEN part of the file name. Just rename it to something else, right? So just like whatever your username is on your computer, right? Or just your name in general. Try renaming the file, and that should help it show up, right? So then once you've added the file here and you've done apply and OK, then you need to restart Multisim. And then once you've done so, then you should be able to go to place, and then go to database, go to user database, and then you should see our new MOSFET models right there, right? So then this custom model instructions file also talks about how to actually edit the NMOS and PMOS transistors to follow the devices that we use in lab, right? So what you're going to want to do, right, is that when I click on our device, right, and then over in this menu, you can change, the length and the width and everything else, but we don't want to change these parameters, right? We're just going to keep these exactly the same. What we're going to do is that we're going to go to Edit Model, right? And then all of these parameters that you see here on the guide are also going to show up, right? And then in here, if we want to model the 2N7000 NMOS transistor, right, then you're going to go ahead and add your values right here. So we're going to change our threshold voltage to 2 volts, right? We're going to change the beta, which is the KP right here, to the value that they specify right there. So 102E-3, right? And then lastly, you might want to also add the lambda as well, although this should really only affect AC calculations, which we're not doing, right? For reference, lambda is the MOSFET equivalent of early voltage, right? So don't worry too much about this right now, but we do want to add this just to keep things as realistic as possible, right? And then if you want to model the other devices, the CD4000N and the CD4000P, right, then you would also just change these values as well. Keep lambda at 0.1, right? And then don't forget this step. Make sure that for the PMOS devices, you put in the threshold voltage as negative. This is important, otherwise the devices will not work properly in the model, right? So then once you've done this, you just click Change Component, and then you click OK, and then now these parameters should be embedded in here, and everything should work just fine, right? So then once you've done that, now you have the devices that you need to use, right? So after this works very similarly to Lab 7 actually with the BJTs, right? So you'll go ahead and draw the schematic, right? Perform the DC sweep, export the data to Excel, right? And then you're going to go through with finding the threshold voltage VT and the transconductance parameter as we talked about before up here when we were doing the characterization, right? So you'll plot the drain curve versus the gate to source voltage, right? And then you will go ahead and take the derivative of that. So just do the pointwise derivative where just like it's shown right here, right? Plot that curve as well, and then you should be able to estimate what VT is, and then you should be able to estimate what the slope is, the maximum slope, in order to get your transconductance parameter. Okay, and then once you have that, you should actually get numbers pretty similar to what we put in here in the model, right? We're just trying to confirm that the model is working properly, so you should get pretty similar numbers. If you don't, then you want to double check to make sure that you went through the correct process, right? And then once you've done that, then you are done with your pre-lab. And this is very similar to what we will be doing in lab, just like in Lab 7. Okay, well, that should be everything you need. Thank you very much.